Everybody, this is the last part of this unit on machine learning and cloud services covering aspects of Kmeans. And this time is a very short section giving some hints as to what happens when you do parallel computing, which in many practical cases you do because Kmeans is so easy to parallelize, and it is in some sense necessary to get decent performance on large jobs with millions or tens or hundreds or billions of points. So we don't really go into any detail. I have other talks which give more detail. This is just a hint as to what you do, and there is some Python code on the GitHub which gives more details. So here we are, parallel computing for Kmeans. So first, we take the sequential version, the Python code, and we need to make a minor change. And that change is to allow the parallelization to be straightforward, effectively using MapReduce. And we first, this is now sequential code. We do the change we do is we don't calculate the actual contribution to the center immediately, but rather we just associate the points to centers and find the contributions to centers as the sum over point vectors. We don't divide by the number of vectors. That's because when we do it in parallel, we'll have lots of these sums. We have to add them up and then divide by the total number of points. So we do two sums: the sum over point vectors of the points, and we also calculate the number of points associated with each center. And if we're doing some non-trivial method of stopping the K-means when the change reaches a certain value, well, we have to calculate the contribution to change from the points. Then this sequential code, as long as you write it like that, can easily be parallelized because all we have to do is do several such calculations of the associated points. Doesn't change at all when you parallelize it. The sum over point vectors doesn't change. The sum over number of points doesn't change, and the sum over error doesn't change. All you have to do in parallel is to do these independently for different sets of points and different processors. And then in the reduce step, you just sum up, calculate the sum over centers, calculate the sum over points, and calculate the sum over errors. And then you do various bookkeeping, such as deleting zero-size clusters. You check convergence and return the best solution based on the quality criteria. So this minor change in the sequential version allows this simple MapReduce version of parallel K-means. Supposing we have P cores or P processors of whatever type they are, we divide the data into P parts. We run P separate maps, each having all the centers, and calculating the contribution to the center from the points in that processor. We sum the P versions all up in reduce. The maps can run trivially in parallel. The reduce is a very simple reduce. It can run in a single process unless you have huge levels of parallelism. And the sequential code can use the mean directly, but the sums must use, but the parallel version must use sums and make a mean after everything's summed up. And then they say we divide by the total number of points in the reduction phase. So this can make some general remarks here. This is the last slide of this unit. So it illustrates some general principles of parallel computing. One is data parallelism. You divide the data into P parts and put one part in each of the tasks, and then you run those tasks independently. If you want to get equal work for each task, then you put equal number of points in each part, and then you use the owner computes rule. The processor that owns a given point does the computation for that point. It decides which center it's near and adds its contribution to the value of to the contribution to the center, which is going to be the overall mean for points in the summed overall processors. But the contribution from the points in processor P is done by processor P. Notice that this has to have the centers present in all tasks. We use an update, we use some broadcasts after the update, or in MPI language we use all reduce, which are not reduce. Okay, that's it, and that's the end of this presentation and this unit. And this shows a picture of the tasks and the data partitioned and the data is associated to the task. That's it. Thank you very much.